Happy morning, students. This is N. Meena, Assistant Professor, Department of Mathematics, JJ College of Arts and Science, Pudukkottai. Today we are going to see a concept types of constraints. It is a core paper in first MSc Mathematics, and that the paper title is Mechanics. We are going to discuss a new topic, holonomic and non-holonomic constraints. So the constraints can be divided in many ways. In one way, it is said to be holonomic and non-holonomic constraint. In other way, it can also be defined as scleronomic and renomic constraints. First, let us see this type, holonomic and non-holonomic constraint. So the equations can be expressed in the form of this type, that is the coordinates x1, y1, z1, x2, y2, z2, xn, yn, zn and t. The time may occur in the case of constraint which may vary with time. These type of constraints are called holonomic constraints. That is, the example is this equation, xi minus xj the whole square. These are all examples of holonomic constraints. So constraints which can be expressed in this manner are called holonomic constraints. All the above examples we involve are holonomic constraints. Then constraints which are not expressible in this fashion are called as non-holonomic constraint. So up to this, this is the definition for holonomic constraint. So you have to write from equation 4. You should not write. You have to write the equation 4 once again. There you have to mention that this equation and you have to write this sentence. Then you have to give an example of the above 4 example. You can give the third example for holonomic constraint. Then you have to come to the non-holonomic constraint. In the next line you have to write constraints are not expressible in this fashion are termed as non-holonomic. The motion of the particle placed on the surface of a sphere. This is a sphere. For example, you can take ball as a sphere. Under the action of some particle is moving under the action of the gravitational force like this. Is bound by non-holonomic constraint, for it can be expressible in the fashion r square minus a square greater than or equal to 0. Here there are greater than or equal to 0 sign. Here time is not involved. Here radius is involved. So equality sign, when the particle slide on the surface of the sphere, you will be getting equality sign. When it on sliding, if it goes outside, then it will happen to be greater than symbol. And when it leaves the sphere, when it is contact with the sphere, the sign will be equal to. When it is leave out of the sphere, it will be greater than. The constraint involved in the motion of the molecules in a gas container. You have to take a gas container and the molecules in a gas container moves. That is the best example for non-holonomic constraint. An object rolling on a rough surface without slipping. So there is a rough surface. A particle is moving in a rough surface without slipping. This is also an example for non-holonomic constraint in the description of motion. So for a non-holonomic constraint, this is the first example. This is the first example up to here. Then this is the second example. This is the third example. So there are 3 examples for non-holonomic constraint. Sometimes the constraints are specified by the restrictions on the. So the restriction are called the constraints on the velocity rather than on coordinates. So if you have x1, x2, they are called coordinates. If it is velocity, then it will be x1 dot. Displacement, rate of change of displacement is the velocity. So if the restriction is involved on the velocities rather than on the coordinates, and still the constraints are can be holonomic. So we have already seen that in holonomic the coordinates will involve. In sometimes the velocities can also involve. The fact is that the velocity equation is integrable. So if you integrate the velocity, you will be getting the coordinates. When x1 dot is integrated, you will be getting x1 integrable to yield a relation of the type 4. For example, so this is the, even though it involves velocity, we can say it as a holonomic constraint. It can be derived into equation 4 by integrating. Now we are seeing an example for that. Let us consider a cylinder of radius. You have to take a cylinder. The radius of the cylinder is taken to be A. Radius of the cylinder is taken to be A, and it is rolling and sliding down an inclined plane. Now we are going to roll the cylinder in an inclined plane. So inclined plane will be in this form. So in this we are rolling this cylinder with this axis always horizontal. So we are moving it in the horizontal way. The position of the cylinder can be located by two coordinates. One is S and the another one is theta. Whereas the distance of the axis of the cylinder measured along the inclined plane that the cylinder has moved, and theta is the angle. So here S and theta are involved. Angle that a fixed radius in the cylinder has rotated from the radius to the point of contact with the plane. If the cylinder happens to roll without slipping, so the cylinder moves in the inclined plane without any slipping, without falling down, then the velocities S dot and theta dot are such that S dot is equal to A into theta dot. So here they have given how holonomic word arises. Holo means, it is a Greek word, it means whole. We are taking the whole part. Whole part is nothing but integrable. We can integrate that. So S dot, here the coordinates are not involved, here the velocity is involved, but if you integrate, you will be getting the ds by dt is equal to A into, instead of S dot you can write ds by dt is equal to A into d theta by dt instead of theta dot. So if you integrate this equation, the differentiation and integration get cancelled, and you will be getting differentiation and integration get cancelled, and you will be getting S is equal to A theta, but plus A theta when comes to this side will become minus A theta, and on integration you get a constant term which is written as S minus A theta is equal to constant. This is the fifth equation. There are however such systems in which equation among velocities cannot be integrated to give a relation between coordinates as above. So here we have taken the velocity and we have arrived at the coordinate. If we can't able to arrive at the coordinate from the velocity, then such systems are called non-holonomic constraints. This is one type. For example, in dishes you may say there are two types, one is vegetarian and another one is non-vegetarian, and you can differentiate food into oily food and non-oily food. In a similar manner, the one type of constraint is holonomic constraint and non-holonomic constraint. The next type we are going to see is scleronomic and renomic constraints. This is another type of constraints. If the constraints are independent of time, so if time is not involved, they are termed as scleronomic, but if they contain time explicitly, so there are two terms, one is explicit, another one is implicit. Explicit means you can able to see clearly, implicit means it is inside, you can't able to see it. So if it is explicitly in terms of time, independent of time, they are, if it is independent of time, it is said to be scleronomic. If it is dependent on time, then it is said to be renomic. A bead sliding on a moving wire is an example for renomic constraint because they are time dependent. As time changes, the position of the slide also, bead also changes. Therefore a constraint is, so the how we can define differentiate constraint is, one type is scleronomic or renomic, another type is holonomic or non-holonomic. Constraint which do not explicitly depend on time are scleronomic, which are dependent on time are renomic. Constraints which are independent of velocities are holonomic, which are dependent on velocities are non-holonomic. These relations are reducible functions of velocities. So these are dependent on velocities. Thank you students for watching my video.